So in the energy conversion diagrams, I'm going to draw the first shape, which is an inclined plane. So let's say we have an inclined plane that looks something like this. And upon the inclined plane, we have placed an object, and the box has to move from point A towards the point B. And meanwhile, as the box moves from point A to point B, you're provided with some of the data here. Let's say the height of this thing is 10 meters. The vertical height is 10 meters. And this angle is given as, let's assume, is given as 60 degrees. And you push the box from A towards B. So you'll have to do some of the work to make it move from A to B. So that work done needs to be calculated. So this is a case 1. And some of the data that is given in the question is the mass of the block. All right, 5 kilograms. And there is some frictional force as well. Okay. And the box covers some distance along the slope, x meters. It's not given numerically. We'll have to sort it out if we can. So it's given x meters. So we need to find the work done as the block moves from A to B, provided the block moves with a constant velocity or constant speed. So velocity or speed in that case will mean the same thing because we are already moving in a straight line. So we can say the box moves with a constant speed or constant velocity. The work done in that case equals the energy changes on the object. The work done equals to the energy changes on the object. So part of your work done would be used to change the kinetic energy of the box. So part of your work done would be used for this thing. Part of the work done would be used to increase the gravitational potential energy of the box, and part of the work done would be used to overcome the friction. So some of the work would be done against the friction, and that would be the work, or that would be the energy that is dissipated in form of heat, because whenever you do the work done against the friction, then as a result the energy dissipated in form of heat. So let us find the sum of all of these. Let's start off with the first thing. What is the change in the kinetic energy of the block? What is the change in the kinetic energy of the block? Now you realize this thing. If the block is moving with a constant velocity, then whatever the kinetic energy was at A, the kinetic energy at B is also the same. So let's say the kinetic energy was 100 joules here. So the kinetic energy would still be 100 joules over here. Why? Because the velocity is constant. For change in kinetic energy, there has to be change in the speed. So say there is no change in the kinetic energy, no component or no part of your work done would be lost to change the kinetic energy of the block. So we can say that the kinetic energy would have no change, hence we can write 0 here. Plus, what would be the change in gravitational potential energy? So at this point, there is no gravitational potential energy because it is at the ground. The height is 0. So at the point B, it would gain the gravitational potential energy, and we can sort it out by the formula. GPE equals mgh, and the mass is 5. G is taken as 9.81. You'll need the calculator. Times the height would be taken as 10 of the work done. that would be used to increase the potential energy. So you'll have to do the work done in such a way that you compensate for all of these. So whatever the total energy we get here, the sum of all these energies, that much work has to be done by you. Now let's find out the work done against the friction. So the friction force, if the block is moving upward, like this, it's moving upward, then the friction force would be in this direction. And if we know the distance along the line of force, we can find the work done against the friction. So friction is there as the block moves from A to B. But do we have the distance on that line? Well, we are provided with this expression that the distance is x. Now, is there any way, so x in that case, you can, if you see it properly, you can call that x equals to the hypotenuse of this right angle triangle. So are we in a position to find the value of that hypotenuse? Do we have enough data? What if I use this thing, sine theta? So sine of 60 equals perpendicular. This is your perpendicular and this is your hypotenuse. So perpendicular is 10 and your hypotenuse is x. So what do you do is x equals to 10 divided by sine 60. Then you hit it on the calculator. Let me know what do we get. Right, for the work done against the friction would be the frictional force, which is 30, times the distance in the line of the friction, be 30 times 11.5. Your work has to compensate for the change in kinetic energy. In this case, luckily there was no change in kinetic energy, so you don't have to do any extra work, but you'll have to compensate for the increase in potential energy, because you have to, not only you have to move it forward, you have to move it to a certain height as well, and then you have to do some of the work against the friction. Yeah, the point X and point Y, these are 30 meters apart. So they can ask this question in two different ways. They can either say find the work done against friction, or they can ask you how much energy dissipated as heat. And we are provided with this thing that the box moves from X to Y with a constant speed in a straight line or with a constant velocity. So you need to find the work done that would be there against the friction. So what is the general expression? Once again, the general expression is the work done. When you're doing the work, you'll have to compensate for all the energy changes. So delta KE plus delta GPE plus the work done against friction. So out of these 1, 2, 3, 4 quantities, which one do we need to find? Well, we need to find this one. But can we find the work done? Yes, we can find the work done easily, because we'll have to apply this much force in order to compensate for everything. The change in kinetic energy, the change in gravitational potential energy, and for the work done against friction as well. So this is kind of a reverse question. So you are provided with the work done, which in this case would be the forward force, which is 5,000, times the distance covered in the direction of that force or parallel to that force, 5,000 times 30. Well, there is not going to be any change in the kinetic energy because the velocity does not change, the speed does not change. How do you find the change in kinetic energy? You find the kinetic energy at x, then you find the kinetic energy at y. Because the speed is constant at x and y, the mass is constant at x and y, so there would be exactly the same value. The kinetic energy would be same at x and y. So what is the change? 0. Now what is the change in the gravitational potential energy? That equals to mgh. So mass times g times h plus what is the work done against friction? Well, we don't know, so we can find it out. Matter of fact, this is what we need to find. All right, so here we have the next situation. So we need to find the work done from A to B. So that needs to be found out. So work done, let me write down the general expression. Work done equals to the change in kinetic energy. You'll have to pay for the kinetic energy change. You'll have to pay for the gravitational potential energy, and you'll have to pay for the work done against friction. So you'll have to pay for these three things. So in this case, the work done against, the change in kinetic energy is not zero. So what is the change in kinetic energy? Well, the change in kinetic energy is the kinetic energy at this point minus the kinetic energy at the other point, the difference of these two. So generally, the final one, which is greater in that case, we write the kinetic energy at that point first, and then we write the kinetic energy at the point A, which is smaller, and that was the initial kinetic energy. Then we subtract these two. Now you have two options. Either you find the change in kinetic energy manually, like at different points, or you can directly find the change in kinetic energy. So what do? Can you quickly find the kinetic energy at point A? And how do? You use the formula 1/2 mv square. So for the point A, it would be 1/2. The mass is 10. The square of the speed is 5 square. You can check out this one as well. And if I find the kinetic energy at B, now what is the change in kinetic energy? You see, through your work done, you don't have to pay for all 720 joules kinetic energy, because there was already some kinetic energy at the point A. So that 125 joules, you didn't have to pay through the work done to get this much kinetic energy. So this one was already there. But what's the change? You had to increase only from 125 to 720. So what is the change? You subtract these two. So delta KE equals 720 minus 125. Now if you want to do it directly, what you write here is 1/2 m, since mass is constant, and then in the brackets you write v square minus u square. That will give you the change in kinetic energy. Now what is v? The square of 12 would be v square, and the square of 5 would be u square. And for all of it, you'll be getting the same answer. Plus, what is the change in gravitational potential energy? That equals to mgh. So mass was 10, g is 9.81, and height is 10. Plus, what is the work done against the friction? Well, 50 times 100, or 100 times 50. 100 is the friction force, times 50 is the distance in the line of the friction. So this is the work that you have to do to make the object move from A to B. So this is the next case that we have. So ball rolls from this end X, from this point all the way towards the bottom of the inclined plane, and we need to find the speed of the sphere at the point phi. And like I said, the inclined plane has a smooth surface, so there is no friction. And some extra details are, so what I generally advise is, whenever you have a situation when you're moving from a higher point towards a lower point. Then instead of writing the expression in terms of the work done, because in that case you don't have to give the driving force. And matter of fact, the work would be done by the sphere itself. In this kind of situation, whenever you're coming from a higher point towards a lower point, down the slope. So what you start off with is, and what kind of energy the sphere would have once it reaches the ground at the point y. So the expression for the potential energy would be mgh equals 1/2 mv square. Since the surface was smooth, so entire gravitational potential energy has been converted into kinetic energy. If the surface were rough, then part of the GPE would have been converted or would have been dissipated in form of heat, and only a certain portion of that GPE would have been converted into KE, which I'll show you in the next case. So what do we need to find? We need to find speed from here. We can do some of the cancellation, like mass cancelled out on both sides, and we write v square equals to 2gh, and then we can take square root of it. So 2 times 9.81 times height is 40, then you can take square root of it. Let's check out the next case, number 5. So I'm going to draw the inclined plane. And we need to find the speed. So what do we do in this case? Once again, whenever we are coming from a higher point towards a lower point, we generally start off with the expression energy at A equals the energy at B. Now what is the energy at A? It would be the gravitational potential energy. And what is the energy at B? That equals the kinetic energy. Now in this case, these two are not equal. In matter of fact, as the ball rolls down the slope, part of your GPE would be converted into, would be dissipated in form of heat, because the work would be done against the friction as well. So we add the work done against friction at the end y. So this was x and this was a point y. So what we do is we find the energy at x, which would be the gravitational potential energy, and that should be equal to the kinetic energy plus work done against friction. The question could be, and this is a common mistake, many of the students are tempted to write work done against friction at the point x, at the starting point in this case. But think about it, the work done against friction would feel to you in the form of heat. So if you think about it, the ball is at rest at this point, the sphere is at rest, and after rolling down the slope, the sphere reaches to the point y. What is the point? Is it x or is it y? At what point would you feel that the sphere is heated up because of the friction? Would that be the point x, where the sphere is not even moving? Or would that be the point y, where the sphere has moved, traveled through the point x, it has faced the friction, is that it has experienced the friction. In matter of fact, this is a point where if you touch the sphere, it would be slightly heated up. So you'll have to add the friction towards the final side. Now what is the work done? Sorry, what is the change in GPE? That is mgh. So 10 times 9.81 times 50, and that equals to KE, which is 1/2 times 10 times v square plus work done against friction, which is 20, times distance is 12. From here you can find v square, find the answer for v square, and then find the answer for v. Hit it on the calculator. So first you sort out this thing, then you subtract this thing on the other side, then 5, we get 5 here. This 5 would be divided on the left side. Alright, so this would be the final speed as a ball rolls down the slope. Let's discuss the last case, which is case 6. So we do have the same thing. And what we need to find is the final speed of the sphere as it goes up the block towards the point B. That needs to be found out. Friction force is there. The change in kinetic energy would be there. Obviously, the initial speed is different. The final speed is different. The work would be done against the friction as well. Now we'll have to write the expression for the energy changes. So the expression for this one would be, once again, you can write it this way. The work done, if you're moving up the slope, you can write the expression for the work done. So work done equals, you'll have to compensate for the change in kinetic energy, delta KE, plus you have to compensate for the change in GPE, plus you'll have to compensate for the work done against friction. And matter of fact, if you want to write for the energies as well, you can generate an expression for the energies as well if you want. For example, what I can write is energy at A. So this is one of the expression. We can always use this one. Matter of fact, we'll go with the expression number 1 to find the kinetic and to find the speed at B. And let me insert the values first. Work done would be the driving force. This is the driving force, the forward force, 500. So 500 times the distance is 30. The change in kinetic energy would be 1/2 times mass times v square minus the initial speed, which is 10 square. And matter of fact, v square needs to be found out. V needs to be found out. Plus GPE, which is m. So 5. G would be 9.81 times h would be 8 plus work done against friction. So what is the frictional force? It is 200 times what is the distance in the direction of the frictional force? 30. So you'll have to sort it out to find the value for speed. And from here you can easily find the expression for the speed at the point B. It's just a question of mathematics now. So what I'm going to do is I'm going to write the expression for the energy changes. So let's forget this method. What I'm going to write is energy at A equals the energy at B. Think about it. All the energies at A equals all the energies at B. Now my question is, what is the energy at A? First of all, energy at A equals to the work done, because at A you're applying a forward force which is 500 and the distance would be covered in the direction as well. So this thing plus, is there any other energy at A? Think about it. that since at A the sphere is not at rest, so it must be having some kinetic energy as well. And how do we find it out? We find it out by 1 over 2 mv square. And what is the speed at A? 10. So if you hit it on the calculator, some kinetic energy at A. So let's talk about the energies at B. So what kind of energies do we have as the sphere moves to the point B? The most obvious one would be as it gains the height, so it would be gravitational potential energy plus the work energy would have been dissipated in form of heat as the ball travels from A to B. It would be heated up and the work would be done against friction like this, because the friction force acts from A towards B. There might have been some friction previously as well because the ball is already coming with a velocity of 10 meters per second, but the friction force that we are provided is the friction force that acts as the ball rolls from A to B. So we don't care about whatever the friction was previously. For our case, the friction is 200 and it is from A to B. Plus, at B, the ball has a kinetic energy as well. It would be having a different speed, so we can write kinetic energy at B. So let's sort it out. So what is the work done? So let me write down the expression. 500 times 30 plus the kinetic energy I already solved for it, 250, equals mgh. Mass was 5, so 5 into 9.81, and h is 8 plus the work done against friction, which would be frictional force, which is 200, times the distance in that direction, plus the kinetic energy at B, 1 over 2 m, but we don't know the speed at B, so we'll write v square. So what I want is, I want you to find this value for speed from the second expression as well as the value for speed from the first expression. Not the expression, I mean the value for speed.